So in this lecture segment, we're going to be looking at distribution protection operation. And I've got this broken into three different parts. The first part's just going to be an overview on distribution protection, where we're going to be discussing some basics such as sensitivity and selectivity. And we'll also talk about the most common type of schemes that are used on distribution, which are related to overcurrent protection. In the second part, I'm going to discuss the various types of devices that you'll see. That would be the breaker in conjunction with the relay, the recloser, and also the fuse. And the third part, we'll get into protection coordination and talk about what has to be the relationship between the breaker and the downstream recloser, the recloser and downstream fuses, and what sort of relationship do we need to get several fuses to coordinate with each other. The objective of the lecture is basically to give you the material you need on protection to understand material that we're going to have in future lectures. And so this isn't really a lecture on protection in the sense that we're going to get into how we set the relays up and how we specifically select the fuses. But it's important to know how protection operates, because when we get into distribution system reliability and power quality and how automated fault location, isolation, and service restoration schemes work, or what we have to be concerned about when we try to integrate distributed energy resource devices, you need to understand how the protection works. And so just be aware that what I'm trying to do is I'm trying to discuss protection operation as opposed to protection settings. And protection settings would actually be the scope of another class that we have at NC State. So this shows the various elements that we're going to see on a set of distribution feeders related to protection. We've got the substation at the top of the circuit. And so we've got the substation transformer shown here. And then the transformer is connected to a bus where we interconnect the various feeders that are going to be coming out of the substation toward the load. And each feeder is going to have its own top of feeder circuit breaker. And so that's actually shown here at the very top. At a very minimum, these distribution circuits would need to have a top of feeder circuit breaker and fuses. And so when we have the various laterals come off of the main feeder, they could be single phase, they could be two phase or three phase laterals. Each of these laterals is typically fused. And what we basically want to see happen is if we have a fault in the lateral, we clear the fault by blowing the fuse, where if we have a fault on the main backbone, then that's going to require an operation of the feeder circuit breaker. Now, we can break this feeder into different zones. And so if we had a fault at the end of the circuit, instead of outaging the whole circuit by operating the top of feeder circuit breaker, we could simply have operation of a line recloser instead. And so if we wanted to break this into three different protection zones, say like zone 1, 2, and 3, then we could improve the performance of the circuit with respect to reliability by breaking it into these smaller zones. And then another thing we need to be looking at when we have these line reclosers is then we want to start looking at the use of different speeds for these fuses, so we could have the coordination set up in such a way we can do something called fuse savings, and we'll talk about that a little bit later on in this lecture. I'm just going to be focused on looking at devices that could break a fault current for now. And so there's also sectionalizers and switches in the circuit, but let's just focus on the devices that could actually break a fault current. For the goals of protection, the first, I guess the highest ranking goal would be safety of personnel and the public. And so we just want to make sure that nobody's going to be injured or maybe even killed as a result of having a short circuit. Then we start to consider the protection of equipment and property. So we want to make sure that we're not going to be, say, like burning out a piece of equipment, say like a transformer. Once we met these goals, then we can start to look at the impact and reliability. We haven't talked about this yet, but we're going to have outage duration and frequency um, of interruption metrics that we want to try to minimize through the proper use of protection on the circuit. And then finally, we would also be concerned about power quality. This gets into what we would call momentary operations, where we want to be able to minimize number of low voltage sags and also blinks on the circuits that are caused by the operation of protection devices. So there's going to be a variety of trade-offs involved in trying to meet all these different types of goals. And to make these trade-offs, we need to understand what's called sensitivity and selectivity. So sensitivity refers to the ability to be able to distinguish between abnormal fault events and normal load events. So if I, for example, had a large motor connected to this circuit, and if I start this large motor up, then I'm going to have a large inrush current associated with it. Well, we wouldn't want the relay at the top of the feeder thinking that was a fault, right? And so we need to have enough sensitivity where we can distinguish between that motor start event and a fault on the circuit. And let's suppose I didn't have these line reclosers in this feeder on the left. Well, if I had a fault at the very end, way out from the substation, we would want to make sure that that top of feeder relay could still see that fault and operate that circuit breaker. And the challenge is that the further away we get from the substation, the lower the fault current is going to be. And so it gets harder and harder the further we get away from the substation to come up with that differentiation between a load event and an abnormal fault event. But this ability of actually seeing these faults further out from the feeder, that's what's sometimes referred to as reach. And so we, to the extent we can, we want to be able to avoid false trips in the circuit. But the problem we run into is if we try to set the threshold too high, well, we may not see certain types of faults, right? And so this is really the challenge associated with sensitivity, is to be able to tell the difference between fault events and what would be normal load changes. This example here kind of quantifies what we could actually see on a circuit. And so what we have is we have a substation that has a certain impedance associated with it. We have different types of overhead lines coming out of the substation. At the very top of the feeder, we would have the most load, so we have the largest conductor size. As we get further away from the feeder, then these conductor sizes start to drop. So when the conductor sizes drop, the impedances become larger. As we get further away from the substation, we have to consider the line length in here as well. And what this shows is, as if you go from looking at faults at bus 1 to buses 2, 3, and 4, what you'll see as you get further away from the substation is that these fault current levels start to drop. And so we could actually predict what these fault current levels are based on doing the short circuit analysis we talked about in the previous lecture. And we would use this information from the short circuit analysis and coming up with the appropriate protection setting set. Selectivity refers to our ability of just isolating the smallest section of the circuit needed in order to clear and isolate the fault. And so if I didn't have the line reclosers on the circuit, and if I had a permanent fault on this main feeder, I wouldn't have very good selectivity, because basically all the customers on that feeder would be outaged. But if I could put intermediate devices in there, such as these line reclosers, then if I do have a fault, say at the bottom of the circuit, then you only have to operate this closest line recloser, or what we would call a closest protected device, in order to clear and isolate the fault. And so the more devices we can actually put on the circuit, the better selectivity we would have. The same would hold true if I had a lateral circuit, unless suppose I had a fault at this particular location. Well, if I just had one fuse, then the entire lateral would have to be taken out of service by the fuse blowing. But if I could further divide that lateral with multiple fuses, then only this section of the circuit would be outage. And if I had customers connected here, they would still be in service. The problem we run into is when we add these devices in series, they have to be able to coordinate. So we want to make sure that if this fault occurs at this location, that the nearest upstream fuse would blow, not both fuses. And so that's the challenge of adding more devices to the circuit. We need to make sure that they actually can still coordinate. But this ability of having the proper selectivity where we can break the circuit into smaller zones, this is going to be really key, as we'll see later on when we look at the circuit reliability in terms of these SAIDI, SAFE, and MAFE indices. Now, how will we know there's a fault out there? Well, the obvious thing to be looking at would be the current levels. And so what we'd be looking at is we'd be looking at the phase currents. We're looking at the phase A, B, and C currents, say at the top of the feeder circuit. We could look at the instantaneous change in the current. Another useful metric is to look at the ground return currents. This is especially useful because if we have a balanced circuit at the top of the feeder, then that ground current is going to be pretty close to zero, and it's going to be real obvious when a single line or ground fault occurs, because that ground current is going to jump to a really high value. And so we can look at phase currents, we can look at ground currents. The other thing we could do is not just look at the instantaneous current, but we can look at the change in current times time. In other words, we can look at what's called an I²T characteristic. Because if I had a motor start, let's say, well, even though the current's going to jump up temporarily, it's going to drop back down once the motor gets up to speed. But if I had a fault that's going to stay on there for a while, then if I were going to look at I²T, if I could look at that over time, I can make a much better distinction between a fault and say like a load change. And so we can look at what we would call time-overcurrent, and we'll get into this later on in the lecture. We can look at that with respect to the phase currents. We can look at that with respect to the ground currents. We could also maybe look at voltage sags on the circuit. If we have a fault that draws a lot of current, that drags the voltage down, so we can look at sags or voltage imbalance. Another thing we can do is there are ways we can measure the fault impedance. And so if there's a low impedance fault, if we look at the ratio of voltage to current, we could pick up on the fact we have a low impedance. There's something else that we also do nowadays because of distributed energy resources on the circuit, is we're also starting to look at the fault current angles, and we'll get into that later on. Because it turns out when there's distributed generation could actually feed current into a fault as well. So nowadays, not all the fault current comes from the substation. It can actually come from distributed generation that's located on the feeder. So that makes the protection a little trickier sometimes. And so the most common type of protection functions that we're going to see on a distribution circuit are going to be related to the use of overcurrent protection. It's pretty convenient to use it in distribution because we've got radial circuits in nature. And so typically the bulk of the current comes from the substation, and it's fairly low cost, and which is important when we have a lot of circuit miles of distribution. But the thing we need to make sure of is that we can meet our sensitivity and selectivity requirements. And so this takes quite a bit of engineering in order to do this. But it turns out that we can do time current protection and coordination actually pretty effectively. We've got a lot of history of doing that and a lot of good different techniques and tools to apply for doing that. And so what we need to have as far as the information in order to do this sort of protection settings is we need to consider the various types of faults that occur. We talked about this in a previous lecture, line-to-line faults, line-to-line-to-line faults, single line to ground faults, etc. And then once we know the source impedances and the line impedances, then we can calculate what types of currents are going to occur due to the faults and what types of currents the relays are going to be seeing. And so if we know the normal load current levels, we can take into account the impact of distributed generation. If we have a range of fault impedances we could use, they're not always zero. That could maybe be high impedance faults, say like 40 ohms or maybe even 100 ohms. Then we can actually use our short circuit analysis to determine all these different currents and then use this for the protection settings. And so if we're talking about a feeder circuit breaker, this would be the types of measurements that you would be using for this. A 52, this is an ANSI device type that represents a circuit breaker. And then what you see here is you see three currents being measured. You're measuring a phase A, a phase B, and a phase C current. And so if you have these connected in Y, you can also get the series combination of these currents. That'll turn out to be the neutral current. And then if you want to use overcurrent protection, what you would enable in your relay is you would enable what's called the instantaneous overcurrent 50 and the AC inverse time overcurrent 51 functions. And so these are ANSI code numbers that correspond to different protection functions. These are actually defined in the IEEE standard C37.2. And basically these CTs or these current measurements would be in the bushings of the circuit breaker typically. And what we would do is we would feed these back into the relay in order to make decisions on tripping the circuit breaker. If we had to use differential phase overcurrent protection, this would be a 67 function. So we're not going to get into all these ANSI functions here, but basically just be aware that you have a variety of different protection functions supported in these relays. And typically what we would be using is the overcurrent functions, which are the 50 and the 51 ANSI device functions. This shows an example of the time overcurrent characteristics associated with a fuse, which is shown on the bottom, and a relay, which is shown at the top. And what you'll see for the fuse characteristics, this is for what's called a 50T fuse, is we'll see that this starts to melt when we hit 100 amperes. And so what we say in this case is the pickup is 100 amperes. And this is 2 times you can think about the nominal current, right? So if this was designed to go on a 50 ampere lateral, we would actually want to have this start melting at 2 times this level right here in order to give it some margin. What you'll see when you look at these fuse characteristics is you'll see that the time it takes for the fuse to melt depends on the level of the fault current. And so it would take a really long time if we were, just above 100 amperes. But if we were at 1,000 amperes, it would only take, a little over 0.1 seconds to blow, right? Where if we're at 10 times 1,000, that would be 0.01 seconds roughly. And so these are the inverse time characteristics that are associated with time overcurrent types of devices. Now, if we had a circuit where we had laterals that were protected by fuses, we would obviously want that fuse to blow first. But if there's something wrong with the fuse, then we would want to have that backed up by the top of feeder circuit breaker and relay. And so what we would see is we had 1,000 amperes, and if for some reason this fuse didn't blow at about 0.1 seconds, then this top of feeder relay would actually be picking up at 10 seconds. And so another thing you'll see when we do protection on distributions, we always want to have a backup. if the primary protection device doesn't work, we want the secondary device in place in order to pick up. And many times we also have a tertiary, even a third device. So again, the challenge here is to make sure we have enough sensitivity in order to see these various types of faults. For example, if a top of feeder relay couldn't see a fault at the bottom of the circuit, perhaps we'd have to make sure we had a recloser there in order to, make sure we can clear that fault. And again, the other thing we have to make sure of is that we have the proper selectivity. And again, what we have to watch out for is we can put a lot of different devices out there to get this selectivity set up into smaller zones, but we have to make sure everything properly coordinates first. In this class, when we get into the reliability, a lot of times we're going to be assuming that the protection operates perfectly and that the nearest protection device is going to operate. But this isn't always going to be the case. Sometimes we find out for whatever reason that you're not properly coordinated. Before I end this segment, I just want to mention what typical setting levels could be for relays. And this varies by utility. Each utility has, various strategies they put in place for setting the relays. But a rule of thumb would be that you would want your pickup for relays to be occurring at about 1/3 the minimum fault current. And so you'd get the minimum fault current from your short circuit analysis, and you would use this in coming up with the relay settings. Maybe you may use 50% or a factor of a half, but you want to have some margin in there. Now, the other thing you have to watch out for is if the circuit is out for a long period of time, you have what's called the cold load pickup effect. And what this means is that if you have like a cold winter day, and to say the feeder's been out of service for a couple hours, once you close that top of feeder circuit breaker in, all the devices, all the heating on that feeder is going to start up at the same time. And so you get what we call a cold load pickup or an inrush to begin with. And see, you would have to have something in there that would allow you to provide service to all those different loads until things got back to normal again. So just be aware. We'll talk about this later on as well. For your ground relays, you would have something kind of similar in that you would probably want to have pickup at 1/3 of the minimum fault current level. But depending on the utility, maybe they would use 50% as a guideline instead. So again, this isn't supposed to be a lecture on settings. We're going to be looking more at the operation of the devices, but just realize that there's a lot of work that's involved in doing these settings as well.